Hello everyone, this is Hari Krishna. I am working as assistant professor in ECE department at Saint Martin Engineering College. Now I am going to explain one important device in an electronics industry, that is rectifiers. Now before going to explain details of a rectifiers, so let us know the different types of rectifiers, important of rectifiers and applications of rectifiers. Now we are going to see definition of a rectifiers. Now here the what is rectifier? Rectifier is an electronic device which is used to convert AC signal into pulsating DC signals. Right? That is the definition of a rectifiers. Now types of rectifiers here. Here the types of rectifiers. So here the generally rectifiers are classified into two types: half wave rectifier and full wave rectifier. So these are the classification of rectifiers. Now we are going to explain in detail what is the need of a rectifiers here. So now here in general all the electron devices are working with DC power supplies. Now in olden days all the electron devices are working with the DC supplies with bulky DC power supplies like generators and cells and rechargeable batteries. So these are the drawbacks of a DC power supply. So these are not easy to carry from one place to the another place, and also cost is more. Therefore, in order to avoid that drawbacks, we need to use rectifier circuits here. Now here now I am going to explain what is rectifier and operation of rectifier with the help of block diagram. So here this is the rectifier. So rectifier is an electronic circuit which converts AC power into DC power, just like DC power supply. Here the process of conversion AC signal into DC signal is nothing but rectification here, and these rectifiers are available in different packages, so with different modules. And types of rectifiers here. So rectifiers are classified into two: half wave rectifier, full wave rectifiers and bridge rectifiers. Now here in half wave rectifier we are using only one diode in one direction, one resistor and one voltage source here. Next one is full wave rectifier. In this case we are using one center tap rectifier and one diode, and another one is the another diode D2. So two diodes, one center tap transformer, one resistor we are using here in full wave rectifier. In bridge type rectifier we are using one transformer, one another one is bridge rectifier here. So in this case half wave rectifier means it can handle only half of the input. In case of full wave rectifier it can handle full waveform of the input signal, that's why it is called full wave rectifier. Now we are going to explain operation of a rectifier with the help of a block diagram here. It is a simple rectifier circuit with single diode and which is connected with the series resistor here. So here AC circuit, AC input is applied here. Now we are taking output as a pulsating DC. Our aim is conversion of DC, but output of a rectifier is not a perfect DC. It's a pulsating DC here. Pulsating nothing but here some amount of AC fluctuations present in the output. So that is the unwanted signal. That's why it is called pulsating DC. So this is the input signal we are using here. This is the input AC signal. So after converting, so output will be become like this. This is the resultant output waveform. So output and input here we are getting here just like this. Now half wave rectifier operation is, so what is the operation of a half wave rectifier? See here. So during the positive half cycle here, now I am going to explain operation of a half wave rectifier. So during the positive half cycle, what is the condition of a output rectifier? So during the negative half cycle of a input signal, what is the condition of a output rectifier? Now we are going to see here. So this is the operation of rectifier. So during the positive half cycle here, see here, this is the positive half cycle. So this is a negative half cycle here. So during the positive half cycle, what is the condition of a condition of a output? So during the negative half cycle, what is the condition of a output? Just we are going to see here. So during the positive half cycle, what is happening here? So diode, in general, diode having positive and negative means this is the positive terminal, anode is positive, cathode is negative here. So during the positive half cycle, this is a positive polarity. Polarity of a diode is also positive. Therefore, the diode, it is in forward bias condition. During the forward bias condition, the diode is acts as a short circuit. So because of that short circuit, the entire current is passing through diode towards the resistor RL. When the current passing through a load resistor RL, the voltage is developed across the RL here. That is the output waveform here. So this is the positive peak cycle. Next, second condition is during negative half cycle, meaning is that this is the during the negative half cycle of a input. So during the negative half cycle of a input, what is happening here? During negative half cycle here, polarity of a diode, in general this is a positive, meaning is that anode. So now here our input is negative. So this is negative and this is positive. Therefore, reversal in polarity, diode become reverse bias condition. Therefore, the diode is acts as a open circuits. So because of open circuit condition, no current is passing through a load resistor. Because of no current is passing through a load resistor, no voltage is developed across the output. So that is represented with this waveform is. So this is the positive wave, output of a positive wave, nothing but during the positive half cycle we will get here. So during the negative half cycle we are not getting output voltage here. So this is the output of a rectifier. Next, so rectifier efficiency. So we need to find the efficiency. So here what is efficiency here? The process of converting entire AC signal into DC signal, that is called efficiency. Meaning is that the ability to convert entire AC signal into DC signal, that is called efficiency. So here what is the efficiency of a half wave rectifier? So that is the 40.6% of efficiency. So this is the half wave rectifier efficiency, meaning is that it can able to convert only 40% of DC signal at the output, but it is not entirely converting DC power supply, DC signal at the output. So this is the 40%. So now here the efficiency of a DC signal formula is DC power output power by DC output power by AC output input power. Now we are going to find the efficiency here. Now which is having different types of ripple factors here. So this is the ripple factor is equal to formula IRMS by IDC whole square minus 1, right. So this is by using IRMS and IDC. So by applying values, so we are getting the ripple factor here, that is equal to 1.211. So what is ripple here? Ripple is unwanted AC signal present in the output, that is nothing but ripple. So the percentage of ripple is here 1.211. So this is the ripple meaning is that unwanted AC signal is present in the output. So that is the that value is 1.211. Now I am going to explain efficiency of a rectifier with the proof here. So efficiency of a half wave rectifier. So in general, efficiency is represented with neta here. So its formula is so PDC by PAC into 100. Now we are going to derive the efficiency of a half wave rectifier. The efficiency of half wave rectifier is 40.6. Now we are going to derive the efficiency of a half wave rectifier here. So what is PDC means? DC output by AC input. Now what is PDC here? So DC P power P is equal to VI. Therefore here power P is equal to VI. PDC means average power. Average power nothing but average current, average voltage by average current. Power P is equal to V square by R, meaning that PDC is equal to Vm. So Vm by power P is equal to V square by R, RL. So what is the value of Vm here? So here Vm is equal to Vm square by, what is Vm here? So Vm is equal to what is, so VDC sir, VDC is equal to Vm by pi. So simply in place of VDC, see here, so in place of VDC just we have to substitute formula, that is Vm by pi here. So that is Vm by pi whole square by RL, right? Right? Therefore PDC is equal to Vm square by RL, sorry, VDC. So VDC square by RL. So here VDC is equal to Vm by pi whole square by RL. So this is, we can write it as, Vm square by pi square into 1 by RL. It's nothing but Vm square by pi square RL. So this is the DC output power. Now we are going to find the AC output power here. So PAC. So PAC is equal to VRMS whole square by 2 whole square by RL. So what is VRMS here? So VRMS is equal to, we know the formula. So VRMS is equal to Vm by 2. Just substitute the value of Vm in VRMS. So what is happening here? So in place of VRMS, just we need to substitute Vm by 2. So that is Vm by 2 whole square by RL, right? So it will become Vm square by 4 into 1 by RL. So that is equal to Vm square by 4 RL. So this is the PAC. So this is the value of PAC. So we know the efficiency PDC by PAC. So the value of PDC is equal to Vm square by R square pi RL. Now PAC is equal to Vm square by 4 RL. Now these two are substituting in efficiency. Now therefore efficiency is equal to PDC by PAC. So we know the value of PDC, that is equal to Vm square by pi square RL into, in place of PC, 4 RL by Vm square, right? So therefore efficiency is equal to, so in RL is get cancelled here. Vm square get cancelled. So now here we are having 4 by lambda square, pi square. Therefore, efficiency is equal to 0.46 into 100. Therefore, efficiency is equal to 40.6. So this is the efficiency of a half wave rectifier, that is 40.6. Meaning is that it can able to convert AC power into DC power only 40% of 40.6% of DC power. Right. This is the efficiency of a half wave rectifier. Now we are going to right. So in this case also we have ripple factor. We know already ripple factor formula IRMS by IDC. So we substitute the IM value. IRMS is equal to IM by 2. Next IDC is equal to IM by 5. So that is, these are the formulas. Just substituting in the ripple factor formula, then we get the ripple factor value is 1.2. Next, advantages and disadvantages. So what is the advantage of here? Simple circuit. We are using here simple circuit, meaning is that which is having only one transformer, only one diode and resistor only. That's why it is simple. What is disadvantage here? Efficiency is very low. So that is the 40.6% only, and the ripple factor is also high, that is 1.211. So ripple factor nothing but that is the unwanted AC signal present in the output, right? These are the advantages and disadvantages. And coming to the full wave rectifier here, full wave center tap rectifier. So we know the types of rectifier, half wave rectifier and full wave rectifier. In case of full wave rectifier, again we are classified into two categories, that is center tap rectifier, bridge type rectifier. Now in full wave rectifiers we are going to explain center tap full wave rectifier here. So in center tap full wave rectifier we are using one center tap transformer and two diodes, one resistor here, right? Now here the operation of a rectifier here. So this is the full wave rectifier circuit diagram. Okay. Now we are going to explain center tap rectifier with the help of black diagram here. So here the basic diagram, which is having one transformer, that is center tap transformer, two diodes, diode D1, D2 and resistors RL, load resistor RL. Now here during the positive half cycle, what is the condition of a diode here? So during the negative half cycle, what is the condition of a diode? We are going to explain here. So here the full wave rectifier nothing but it can handle full waveform of a input signal. Now here during the positive half cycle of input, this is input, during the positive half cycle of input, now here the diode D1 is, here the polarity of a secondary winding become positive and this one is top winding become positive, so lower winding become negative. Now during the positive half cycle, diode D1 is forward bias condition, diode D2 is reverse bias condition. So in forward bias condition, diode D1 is acts as a short circuit, D2 it acts as open circuit, meaning is that no current is passing through a resistor diode D2. Now during the forward bias condition, during the positive half cycle of input signal, diode D1 only forward bias, it can act as short circuit, therefore the current is passing through diode D1 towards load resistor RL and towards the ground. So in that case, when the current is passing through a load resistor RL, now here the voltage is dropping across the resistor RL here. So this is the output of a center tap rectifier during the diode D1. So now here during the negative half cycle of a input signal, now here diode D1 become forward reverse bias condition, diode D2 is forward bias condition. Now during the reverse bias condition, diode D1 is acts as an open circuit, this is the short circuit. Therefore the current is starts flowing from D2 towards the load resistor RL and coming towards the ground. So in this case, because of the diode D1 D2 is forward bias condition, current is passing through load resistor RL, then voltage is developed across the load resistor. Therefore during the positive half cycle, again we are getting, during negative half cycle again we are getting the another peak signal here. So therefore during the negative half cycle we are getting one peak here, during the negative half cycle also again we are getting another peak. Therefore it can conduct two half cycles of input signal, That's why it is called full wave rectifier. Now here the main advantage of a full wave rectifier is the efficiency of a full wave rectifier is increases, that is the 81.2% of efficiency, meaning is that it can able to convert the DC energy into AC energy into DC energy up to 81%, 81.2%. Now here, so this is the operation of a full wave rectifier. Next, another one is the bridge rectifier. So in this case, we are using 4 diodes, one transformer here. So during the positive half cycle, what is happening here? What is the condition of a diode? During the negative half cycle, what is the condition of a diode here? We are going to analyze here. Now during the positive half cycle, what positive half cycle of input signal, what is the condition of diode? See here, during the positive half cycle, now here the this diode and diode, this diode and these two diodes, these two diodes become forward bias, remaining these two diodes are in reverse bias condition. Now because of these two forward bias condition, the current is passing through like this here, right? So during this condition, now here the diode is, current is passing through a load resistor RL here, therefore we are getting output across the load resistor RL. Next, during the negative half cycle, what is the condition of a output of a voltage, output of a rectifier here? So during the negative half cycle of a input signal, now here this diode and this diode, these two diodes are become forward bias and remaining two diodes are in reverse bias condition. In this case, so here the current is passing through this diode to the load resistor RL and this diodes to the, this diode and these two diodes here, this diode and this diode, these two diodes are in forward bias condition. So because of these two forward bias condition, current is passing through a load resistor, then the voltage is dropping across the output resistors. Again negative half cycle also we are getting, again we are output waveform. So this is the, in this case two waveforms, in this case two half cycles of input signal is conducted by the rectifier, that's why it is called full wave rectifier. Now here these 4 diodes are connected in bridge structure, that's why it is called bridge rectifier. Now average DC current here, so average DC current formula IDC is equal to 2 Im by 5. Similarly average DC voltage, so here 2 Vm by 5 here. Next load RMS current, that is AC current, that is IRMS is equal to formula, that is IRMS is equal to Im by root 2. Next load voltage, that is equal to Im by root 2 into RL. Next DC output power, so DC output power is equal to 4 by pi square into I square Rm by into RL. Next AC input power, so that is equal to PAC is equal to Im square into RF plus RL plus into RL by 2. So next one is rectifier efficiency. So in this case we have more efficiency compared to the half wave rectifier. Now here the efficiency of half wave rectifier is 81.2%. This is the rectifier efficiency, right? Now this entire operation of a half wave rectifier, full wave rectifiers, I am going to explain with the help of a animation diagram. Right, so this is right. Now this is the half wave rectifier. Now this half wave rectifier is, see here, see this is animation, right? So during the first half cycle, what is happening here? So during the negative half cycle, what is happening here? See here. So during the negative first half cycle of a input signal, now the current starts flowing through the diode here. See, during the first half cycle, then current is starts flowing through it, then voltage is dropping across it. Similarly, during the negative half cycle, what is happening here? See, so during the negative half cycle, no current is passing through it, right? So because of no current passing through it, no voltage dropping is across the output. So this is the half wave rectifier, right? So we know, so we have already seen, so average values, so Vs is equal to Vm sin omega t, so that is the input voltage, Vm sin omega t. So Vdc we know, so Vm by pi. So next, so peak inverse voltage. So what is the peak inverse voltage? Peak inverse voltage is the maximum reverse voltage that can device can be withstand. Right. Next, coming to the full wave rectifier here. Now we are going to see entire operation of a full wave rectifier with the help of animation diagram. See, which is having one center tap transformer, diode D1 and D2. Next, load resistor RL and output voltage V0. This is the input voltage with the represented with the input voltage Vs, right? Next, we are going to see animation here. See, this is the animation picture. So what is happening here? This is the input signal. So this is the output signal. So during the first half cycle, so what is happening here? What type of mechanism existing in the full wave rectifier? So during the negative half cycle, so what type of mechanism is existing in the full wave rectifier? Now we are going to see with the help of animation diagram. Now this is the circuit diagram represented with the animation. See here, this is input signal. What is happening here? So during the first half cycle, what is happening? So here the diode D1 is forward biased and the current is passing through load resistor RL here, right? So during the first half cycle, diode D1 only conduct, therefore the current is passing through diode D1 towards the load resistor RL, therefore we can get the output voltage across the resistor load. Next, during the negative half cycle of a input, so what is happening here? See here. So during the negative half cycle, what is happening? So during the negative half cycle, so diode D2 is on, therefore the current is passing through diode D2 to load resistor RL, therefore voltage is developed across the load resistor RL, that is 2 peaks. So this is center tap rectifier, full wave rectifier, center tap full wave rectifier, because we are using here center transformer. Next, coming to the full wave rectifier with the bridge rectifier, right? Similarly, so this is the bridge type rectifier, because all the diodes are constructing like a bridge, that's why it is called bridge rectifier here. So the efficiency of a bridge full wave bridge rectifier and efficiency of a center tap transformer both are same, that is 81.2%. Meaning is that the ability to convert AC power into DC power, that is 81.2% only. Now this is the full wave bridge rectifier. Now I am going to see animation, right? So this is the animated picture here. So what is happening? So during the positive half cycle of a input, so what is happening during the positive half cycle? So diode D1 and diode D3, these two are in forward bias condition. Therefore, the current is passing through D1 towards the load resistor RL and D3 towards the secondary transformer. So because of that, so here during the positive half cycle, we are getting output waveform across the load. Similarly, so during the negative half cycle, during the negative half cycle of a input signal, so what is the condition of internal mechanism of a full wave rectifier? We are going to see here. Now here during the negative half cycle, see, so during the negative half cycle here, so what is happening during negative half cycle? Here diode D2 and D4, these two diodes become forward bias, therefore the current is passing through D1 through resistor RL and D4 towards the secondary winding of a transformer. So in this case, now when the current is passing through a load resistor RL, now we will get the output voltage here. That is the output voltage. Similarly, here the output voltage Vs is equal to, now here Vs is the input voltage is equal to Vm sin omega t. This is the input voltage, we know that. So this is the VDC, meaning is that average DC voltage, that is 2 Vm by pi. So in case of half wave rectifier, so DC voltage is equal to Vm by pi. So in case of full wave rectifier VDC, that is average voltage is equal to Vm by pi. So that is equal to 0.636 Vm here. So now full wave rectifier bits, now in this case form factor value we have, so that is the RMS value by 1.11 here. So this is the full wave rectifier efficiency and bridge rectifier, right? So today I completed entire version of a bridge rectifier and half wave, full wave and its type, right? Thank you.